Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 6, Lesson 6, More Work with Exponent Properties. In the past 3 lessons, we've actually been developing the 3 main exponent properties, as well as looking at negative exponents and zero exponents. Today, what we want to do is just get a lot more work with all of those ideas. We want you to be very comfortable with exponents, how to manipulate them, how to write equivalent exponential expressions before we move on and start to tackle the really bulk of this unit, which are exponential functions. So right away, let's get into it and review the 3 main exponent laws. So exponent properties are laws. It's important to know and be able to use exponent properties to manipulate expressions involving exponents. But of course, what we first want to do is review those 3 major exponent properties. So that's what we got in exercise number 1. What I'd like you to do now is pause the video and see if you can fill in what each one of those is equal to. Pause the video now and go ahead and do that. All right, now one thing I do want to emphasize throughout all 3 of these is that these exponent properties are true whether the base of each exponential expression is a variable or a number, and whether or not the exponents are variables or numbers. They hold no matter what. So our first exponent property says if we multiply 2 things together that have the same base, we add their exponents. So x to the a times x to the b is x to the a plus b. All right? Our second exponent property says if we have something raised to an exponent, and then that entire expression is raised to another exponent, and you'd be amazed at how often that comes up, then we multiply those 2 exponents together. You know, that might be one that you're like, oh really? Like that matters. But it does. It actually comes up quite a bit. And our final exponent property, which is a little bit dicier than these 2, is when we have x to the a divided by x to the b. So we're dividing 2 quantities that have the same base, and we end up subtracting their exponents. Now, by the way, given the fact that multiplication and division are inverses of each other, it's not surprising that if you add the exponents in the case of multiplying, you subtract the exponents in the case of dividing. The one thing that's, of course, a critical difference between them is that addition is commutative. So whether that's x to the a plus b or x to the b plus a is completely irrelevant. On the other hand here, when we have x to the a divided by x to the b, it is always x to the a minus b. In other words, it is always the power of the numerator minus the power of the denominator. All right, now, because we've got those 3 properties of equivalence, they're equivalence properties, meaning that literally those things are equivalent to each other and therefore can replace each other in algebraic expressions, we can now simplify a variety of things that have exponents. And let's take a look at a few of those in exercise number 2. Rewrite each of the following as x to the n, where n could be either a positive or negative integer. Fantastic, right? So when I take a look at letter A, which is x to the 5th times x to the 3rd divided by x to the 12th, there's quite a bit going on, right? Let me write this thing out kind of in its glory, x to the 5th times x to the 3rd divided by x to the 12th, and let's talk about it just a bit. Some people might say, well, I'm not sure. Should I, divide first and subtract exponents? Should I multiply first and add exponents? Well, the plain fact is, right, replace equivalent things with equivalent things. So if I just ignore the denominator, which I can do, I can say x to the 5th times x to the 3rd is x to the 8th, right? Those 2 things are equivalent. I simply add their exponents. Now, of course, I have a straightforward application of the 3rd exponent property, which says that if I have something to a base raised to a power divided by the same base raised to a power, I can simply subtract those 2 powers, which is going to be x to the 8 minus 12, which is x to the negative 4. Now, some of you may have the urge to then rewrite that as 1 over x to the 4th. And certainly x to the minus 4 is equivalent to 1 divided by x to the 4th. But This particular problem says rewrite each of the following as x raised to the n, where n could be either a positive or negative integer, so I just want to leave it like that, x to the minus fourth. Let's take a look at letter B together, and then I'll have you work on letter C on your own. Letter B. Here I have x to the negative 3 raised to the fourth times x to the fifth raised to the third. Great. Well, the first thing that I'm going to do in this problem is I'm going to take this first expression and I'm going to use that second exponent law that tells me that I can multiply the two exponents together. Negative 3 times 4 is negative 12. I can do exactly the same thing with that second exponential expression, and I'll get x to the 15th when I multiply 5 by 3. But now I have a straightforward application of the first exponent law, which tells me I can add those two exponents, giving me x to the third. All right, so again, each and every time I'm looking at a particular part of the overall expression and I'm saying, can I replace that using one of the exponent laws? And then that simplifies it a bit. Then I use another exponent law, etc., etc. Why don't you go ahead and see if you can tackle letter C? All right, fantastic. Well, in letter C, the first thing I'm going to do is use the third exponent law to make x to the third to the second into x to the sixth. I can multiply those two exponents together. Now in the denominator, I can use the first exponent law. I have to be a little bit careful here because when I add those two exponents together, right, negative 7 plus positive 3 is going to be negative 4. Finally, I can use the last exponent law, the subtraction exponent law, or the division exponent law, depending on how you want to phrase it, to subtract those two exponents. Here I have to be very careful because I'm going to have 6 minus negative 4, which is going to be x raised to the 10th. It is certainly not x squared, right? It would only be x to the second if I had x to the sixth divided by x to the positive 4, not negative 4. All right, so in this case, right, we've used all three exponent laws over and over again to simplify these and write them as equivalent expressions. I mean, it's kind of amazing, right? If you took a number, let's talk about letter B, which I think is a great example. If you took a number like the number 2 for x and you substituted it into this extremely complicated expression, right, that would be ugly to evaluate. If I put x equals 2 in, it would give you the exact same thing as if you just took 2 and you cubed it, right? Never forget that, right? I'm not adding 3 and 5 here. I'm literally saying that this expression and this expression would have exactly the same values for the same value of x. All right, let's keep going. Now, besides being able to manipulate exponent properties, we also want to be able to feel more comfortable with negative exponents. As much as I hate to say this, negative exponents are never going to go away. You're going to continue to use them forever in math from now on, all right? And it's important because we use negative exponents for a whole variety of different things, and we use them all sorts of times and places, and you just have to be ready for them. So let's take a look at exercise number 3, which is purely numerical. Both 3 and 4, purely numerical, no variables involved. Let's take a look at number 3. Write each of the following simple expressions involving negative exponents as fractions. Try to avoid using your calculator when possible. All right, well, why don't we do the first two of these things together, right? So it's very important to note, you know, a lot of times with things like exponent properties, we almost always have the base as a variable, right? Well, what's x to the negative 5? It's 1 over x to the 5th, right? And that's important stuff. It's not that. But many, many times, we're going to use negative exponents in purely numerical expressions. So we want to be able to look at 2 to the minus 1 and go, well, what number is 2 to the negative 1? Well, by the definition of negative exponents, that's 1 divided by 2 to the first. And of course, 2 to the first, that's not working. 2 to the first is just 2. So 2 to the negative 1 is 1/2. And that is critically important. I really want to emphasize something here. These two things are the same number, just written in different ways. And again, you might be like, well, why would I ever want to write 1/2 as 2 to the negative 1? Well, maybe we'll be able to answer that question before too long, all right? But you want to be able to go back and forth between these two. And in fact, in the next exercise, we're going to start with the fraction and try to move backwards to an expression like that. But let's keep going. Let's take a look at letter B. Here we have 4 to the minus 3, all right? And again, just like the previous problem, we start by saying, well, that's 1 over 4 to the third. Now, 4 to the third is obviously a little bit harder to evaluate than 2 to the first, but 4 to the third is 4 squared, which is 16, times 4, which is 64. So 4 to the negative 3 is 1/64. All right, what I'd like you to do is pause the video now and see if you can write out what fractions each of those two expressions are equal to. All right, 3 to the negative 4th. Here we go. Give myself a little space here. This is going to be 1 divided by 3 to the 4th. Let's see, what's 3 to the 4th? Well, 3 to the 2nd is 9, 3 to the 3rd is 27, and 3 to the 4th then would be 81. All right, 6 to the minus 2, that's going to be a pretty easy one, right? Because that's going to be 1 divided by 6 squared. 6 squared is 36. So 6 to the minus 2 is 1/36. All right, so it's one thing to be able to move in this direction, all right? And it's very important to be able to do so. But we also want to be able to go in the other direction. So there are certain times when we can take a fraction, especially what's called a unit fraction. This is what we're going to be doing in exercise 4. Maybe get rid of that blue line. Right? When we have a unit fraction, i.e. 1 divided by a number, where we're going to want to write that as some number raised to some negative power. So let's take a look at exercise 4 and get some practice with that. Write each of the following fractions as a whole number raised to a negative power. Make the base as small as possible. All right, so this is critical. Make the base as small as possible. All right, so let's talk about this. So with 1/9, okay, one thing that is not of any question is that 1/9 is the same as 1 over 9 to the first, which would then be the same as 9 to the negative 1, okay? And that's really kind of what this problem is asking us to do, all right? Now, the one thing about this, even though 1/9 is definitely 9 to the minus 1, it doesn't make the base as small as possible. And let me show you why. So I'm gonna go back on this one a little bit, right? One thing I can do with the number 9 that I want to be able to recognize is that 9 is the same as 3 to the 2nd power, all right? So 1 divided by 9 is the same as 1 divided by 3 to the 2nd. But 1 divided by 3 to the 2nd is, by definition, 3 to the minus 2. All right, and that is as small as we can make the base. So every time that I look at the number in the denominator, what I want to say is, can that be written as some smaller number raised to a particular power? Now, when I look at 1/5, right, and I hone in on the 5, 5 is a prime number, right? There is no way to write 5 as the power of any other whole number other than 5. So 1/5 really is quite quick. That's the same as 1 over 5 to the first, and that's 5 to the minus 1. Okay? Now letter C and letter D, those are ones where you can look at 1,000 and you can actually say, oh, 1,000 is the same as this number raised to this power, and even better yet, 16, right? 16. That's even trickier. You can make into a number raised to a power as well. So I'd like you to play around with those and see if you can make those bases as small as possible. Pause the video now and see what you can do. Well, any power of 10 should be relatively easy for us. In other words, let me get rid of this, right? 1,000 is equal to 10 to the third. So 1 over 1,000 is equal to 1 over 10 to the third, and that's 10 to the minus 3. One of the crazy things is you were learning about negative exponents a long time ago when you were actually looking at powers of 10. This also gets into things like scientific notation and how you use it to express very small and very large numbers. Now, probably the most challenging of them is 1/16. By the way, 1/16 is certainly 16 to the minus 1, just as letter C is 1,000 to the minus 1. 1/16 is also 4 to the minus 2, and you can probably see why, right? Because 16 is 4 squared. But we can even do better than that. 16 is 2 raised to the 4th, right? And that's a little bit tricky, right? But 2 to the 4th is 2 times 2, which is 4, times 2, 8, times 2, 16. So 1/16 is 1 over 2 to the 4th, which then is 2 to the minus 4. Now, I do want to say, if you had 4 to the minus 2 there, by the way, just total coincidence that those numbers would be flipped, but if you have 4 to the minus 2 there, then you absolutely understand what's going on, okay? And I don't want to take anything away from you on that. If you said, oh, well, 16 is 4 squared, so it's 1 over 4 squared, and that's 4 to the minus 2, that's really good, okay? That's really good. That's like 3/4 credit kind of on that problem, all right? But if I want to make that base as small as possible, the smallest base is equal to 2. All right, let's keep going. Exercise number 5. Explain or justify why the expression 1/27 times 3 times x to the 8th is algebraically equivalent to 3 times x to the 5th. All right, this is a direct extension of the work that we just did in the last problem, along with the work that we did with exponent properties in exercise number 2. So I'd like you to pause the video right now and see if you can figure out algebraically why this expression and this expression must be equivalent. Well, the real key in understanding this is understanding how the number 27 and the number 3 relate to each other. That's really key, right? And the plain fact is, right, 27 is equal to 3 to the 3rd, right? 3 times 3 is 9, times 3 is 27. So 27 is 3 to the 3rd. That means that 1/27 is equal to 1 over 3 to the 3rd, which is 3 to the negative 3rd. All right? Now remember, equality, right, and the substitution property of equality now says I can take this expression, 1/27 times 3 to the x plus 8, and I can replace 1/27 with 3 to the minus 3rd. So all of this is going to be 3 to the minus 3rd times 3 to the x plus 8. But now I have this fantastic exponent property. In fact, it's the first exponent property that says when I multiply two things that have the same base, I'm going to add their exponents. So 3 to the minus 3rd times 3 to the x plus 8 is going to be 3 to the x plus 8 plus negative 3, right? I'm just adding this to this, and that is going to be 3 to the x plus 5. All right. But the real key there is understanding how the number 27 and the number 3 relate to each other through exponents, right? Right? It's not just, well, I know that, 27 is 3 times 9. I mean, that's great. It's also 24 plus 3, right? There's a variety of ways that 27 and 3 relate to each other. But the real important thing is, how does 27 relate to 3 in terms of exponents? All right. Let's keep going on this exponent work. We need to be able to use the law of exponents, often multiple ones, to rewrite exponential expressions, right? So this is very, very similar to what we did in exercise number 2, except in this problem, all of the bases are now going to be numerical, and all the exponents are going to have algebraic expressions in them. And yet, the exponent properties are still the same exponent properties. So let's take a look at exercise number 6. Rewrite each of the following so they contain a single exponential expression. Letter A, 5 to the x plus 3 times 5 to the 2x minus 1. All right, so it's straightforward, right, letter A. We've got an exponent property that says when I multiply two things with the same base, I'm going to add their exponents. Doesn't matter what the exponents look like. Doesn't matter whether they're numbers, algebraic expressions, or lemmas. We're going to add them together, all right? So in this case, this is going to be 5 to the x plus 3 plus 2x minus 1. And now it's just about combining like terms. I got x plus 2x, which is 3x. I have 3 minus 1, which is positive 2. So all of that is just 5 to the 3x plus 2. All right, nothing else. Let's take a look at letter B. Letter B, I've got 10 to the 2x minus 3 all to the second. All right, well, I've got this great exponent law. It's the second law that says when I have something raised to an exponent raised to another exponent, I'm going to multiply the two exponents. Again, it doesn't matter what the exponents look like. I'm going to multiply them together. So in that case, what I'm going to have here is I'm going to have 10 raised to the 2 times 2x minus 3. Now I have to distribute that multiplication by 2, and I'm going to get 10 to the 4x minus 6. Okay, let's do one more of them together, and then I'll let you do the real hard one on your own. The real hard one. Okay, let's take a look at letter C. Here I've got 2 raised to the 6n plus 5 divided by 2 raised to the 4n plus 1. Now, you might feel completely comfortable with this exponent law, i.e. when I have two things with the same base that are dividing one another, I'm going to subtract the power of the denominator from the power in the numerator. But you have to be very careful here. Subtraction of an algebraic expression is always a little bit tricky, but I can certainly say in this situation that this is going to be 2 to the 6n plus 5 minus 4n plus 1. And notice how I put that 4n plus 1 in parentheses. That's a reminder that I'm going to have to distribute that subtraction, so that becomes 4n minus 1. Now it's just combining like terms. 6n minus 4n is 2n, 5 minus 1 is 4, so all of that is 2 to the 2n plus 4. Okay, so you could be very comfortable with the exponent property here and still make a mistake in terms of that subtraction because you have to distribute, right, that negative through the parentheses. All right, letter D's got a lot going on, so I want to see if you can weed through it and get that as some kind of final answer as just 7 raised to some expression. Pause the video now and see what you can do. All right, well here, I've got something raised to a power divided by the same thing raised to another power, and then all of that raised to an exponent. Okay? So the first thing that I'm going to do is I'm going to actually tackle what's inside of the parentheses. I mean, order of operations kind of says to do that anyway. So the first thing I'm going to do is use my third exponent law to say, well, what's inside of that parentheses must be 7 to the 2x minus, and again, here we go again, to the x minus 5, and I'll worry about that cubing later on. All right, now what I'm going to do is I'm going to have to distribute that subtraction. So that's going to be 7 to the 2x minus x plus 5 all to the third. All right, that's going to be, I got to get myself a little more room. This is the most lengthy of them all, and now I got to go back up because I can't see my problem anymore. Come on, there we go. So now inside I'm going to have 7 to the x plus 5 all to the third, and now I can use my second exponent law to multiply those two exponents together and get 7 to the 3x plus 15. All right. That one was a little bit more layered, right? Because we had to use first that property that allowed us to subtract exponents, and then the property that allowed us to multiply exponents. Honestly, this is probably actually less manipulation than what we had to do at least in one of the problems on exercise number 2, but it may have been a little bit more messier because the exponents were algebraic expressions rather than just numbers. Okay, we just keep doing them and doing them. Exercise number 7. Use the third exponent property to write each of the following in the form b to the x, where b is some positive rational number. Okay, so let's talk about this a little bit. And I apologize because this shouldn't say the third exponent property. It actually should say the second exponent property. And before we kind of talk about that for a second, what I want to do is I really want to emphasize that second exponent property. That second exponent property said x to the a raised to the b is equal to x to the a times b. Okay, that was the second exponent property, and that's what I'm going to be using right here. The third exponent property was the one that dealt with dividing two things that have the same base. In many different textbooks, those two exponent properties are introduced in possibly the opposite order. I think it's still best to call this the second exponent property. Now, the interesting thing is, I actually, in this problem, want to run the property sort of in this direction rather than in this direction, okay? And in fact, I'm going to take this thing and put it right down there, and even take my little arrow and put it right down there so that I can come back and illustrate what I mean by this. Let's take a look at exercise. Well, actually, we already read through it. Let's just take a look at A. Here I have 3 raised to the 2x, right? 3 raised to the 2x. And notice, right, 2x has this kind of form, 2 times x. So I can actually rewrite this particular problem as 3 to the second raised to the x, right? Certainly 3 to the second raised to the x would apply that second exponent property that would allow me to multiply these. I'm literally sort of, if you will, unmultiplying them. Now, of course, 3 to the second is just equal to 9, and therefore 3 to the 2x is the same as 9 to the 1x. All right, and that's what we're getting at in this problem. Each time I want to use this property, but kind of in reverse, to get back to a single number being raised to x. Now I'd like to take a look at letter B together because that's a little bit tricky for people. Let's take a look at it. Here I have 5 to the minus x. Now that may not seem like it's very similar to what I've got going on down here, right? It just looks like I have negative x. So let me try to make it very clear. This is the same as 5 to the negative 1 times x, right? Negative x is the same as negative 1 times x. And that's something that I hope you're very, very, very comfortable with, right? Just as x is equal to 1 times x, negative x is equal to negative 1 times x. Now, why would I write it this way? So that I can reverse this rule, and I can now say that's got to be the same as 5 to the negative 1 all raised to the x, right? So 5 raised to the negative 1 times x is the same as 5 to the negative 1 raised to the x, but then 5 to the minus 1 is the same as 1/5, and this is really critical. 5 to the negative x and 1/5 to the x are the same thing. 2 to the minus x would be the same as 1/2 to the x. 3 to the minus x would be the same as 1/3 to the x. 10 to the minus x would be the same as 1/10 to the x. I don't think I have to keep beating that one to death, but my point is that is not a situation that comes up just randomly. It actually comes up quite a bit. I love the fact that those two weren't attached to each other. Okay, so why don't you pause the video now and try to do letter C and letter D. All right, so letter C, I have 2 to the 4x. This is a little bit more straightforward of one. That's going to be the same as 2 to the 4th raised to the x. 2 to the 4, as we talked about earlier today, was 16. So 2 to the 4x is the same as 16 to the x. All right, simple enough. And here we have a negative exponent again, but it's a little bit more simple to think about than this one. In fact, I think that we saw this one just a little while ago, or something very similar to it. 10 to the negative 4x is going to be the same as 10 to the minus 4th. To the x, that's going to be the same as 1 over 10 to the 4th raised to the x, and 1 over 10 to the 4th is 1 over 10,000 raised to the x. Whew! 10 to the minus 4x is the same as 1/10,000th raised to the x. Okay, let's take a look at a couple last problems. There's a lot of problems in this lesson. Sometimes we will want to rewrite a whole number as a smaller number raised to a certain exponent. We've seen that a few times today, right? We saw that back, I think, in exercise number 4, where we were trying to take those fractions, right, unit fractions, and write them as maybe like some number raised to a negative power. Well, let's see why we might want to do that. Let's take a look at exercise number 8. Consider the expression 2 to the x divided by 8. Rewrite the number 8 as 2 raised to some power. All right, so pause the video now and see if you can think about what 8 is equal to in terms of 2 raised to some power. All right, well, 2 squared is 4, times another 2 is 8. So 8 is the same as 2 to the third. Or light bulb is the same as 2. There we go. 8 is equal to 2 to the third. Letter B. Substitute your answer from A into the original expression and then use an exponent property to simplify the expression. All right, I'd like you to try that. Pause the video now. All right, well, here we go. 2 to the x divided by 8 is the same as 2 to the x divided by 2 to the third, and that's the same as 2 to the x minus 3. That's it. And again, you could see why perhaps taking an expression like this, 2 to the x divided by 8, and rewriting it as 2 to the x minus 3 might have some advantages in certain situations. All right, last problem. Then I think we will have really kind of worked with the exponents to death. Exercise number 9. Which of the following is equivalent to 25 times 5 to the x? Show the manipulations that lead to your answer. All right, well, I'd like you to play around with this. Hopefully you'll be able to figure it out. All right, well, I'm hoping you got choice 2. Right, the real question again is how does 25 relate to the number 5? How does 25 relate to the number 5? Well, as you all know, 25 is 5 times 5 or 5 squared, right? So I can replace the expression 25 times 5 to the x with 5 squared times 5 to the x. But now I've got that wonderful exponent property, the first one that said that that will be 5 to the 2 plus x. And of course, because addition is commutative, 5 to the 2 plus x is the same as 5 to the x plus 2. All right, and that's it. Let's summarize. Now, we did a lot of problems in this lesson, and I'm sorry it took so long, but it's really important for you to get a lot of fluency both with exponent laws, with both numbers and variables, right? We want to be able to use exponent laws to rewrite both algebraic expressions and numerical expressions in different ways using exponents. All right. Due to the fact that we have negative exponents now, we can do a lot in terms of fractions and things like that, rewriting them in different forms, which are going to become important as we start to manipulate exponential equations and functions. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.